I'm the calculus professor, and today we'll be talking about volumes by slicing. In problem number 23, we'd like to use the disk method to find the volume of the solid generated when the region bounded by y equals 1 over the fourth root of 1 minus x squared, y equals 0, x equals 0, and x equals 1/2 is revolved about the x-axis. All right, so first things first, let's draw a picture, try to get a feel for what the shape looks like that we are spinning about the x-axis. So, here's my xy axis. I've got this y equals 1 over the fourth root of 1 minus x squared. Now, when you get functions like this that you're kind of like, I'm not exactly sure what it looks like, it's okay to plot a few points. It's not such a bad thing. But let's come back to that. Let's look at that last. Y equals 0 is the x-axis. So this is y equals 0. X equals 0 is the y-axis. So this is x equals 0. And then x equals 1/2. Let's just put that right here. This is at 1/2, and that's x equals 1/2. Now, what I'd like to know is, well, what's happening when x is equal to 0? So where does it intersect this vertical line? And you see that that would be at 1. So up here at 1, we get some intersection. And then what's happening at like x equals 1/2? And I don't even have to go into the details very much. At 1/2, that would be a fourth. 1 minus a fourth is 3/4. And then I get like a fourth root of 3/4 on the bottom. I don't care very much. The point is, it's some positive number, little positive number. So it's intersecting like over here somewhere. Now, I don't necessarily need to know what that point is to kind of know that this thing looks something like this. All right. Yeah. And another thing that's helpful here is if I ever got to the point 1, then this would be 0. So this is just kind of headed down to 0 over here. So it looks something like this. And if I were to spin this around the x-axis, then we'd get a shape that looks roughly like . And if I take a cross section, I get a nice disk. All right, so let's find the volume of this shape. So the volume, so this is my region that I'm spinning. The volume is going to be equal to the integral from A to B. Now, A is where I start cutting disks, and B is where I stop cutting disks. So I start at a point, I end at a point cutting my disks. The place where I start cutting is 0. The place where I stop cutting is 1/2. So I'm integrating from 0 to 1/2 of the equation of a disk, or pi r squared. So inside goes pi r, which is, in this case, let's look at just one disk that's setting here at x. One disk looks like this, and the radius of that disk is the functional value. So the functional value in this case is 1 over the fourth root of 1 minus x squared dx. And then I need to take this quantity and square it. So I have a pi r squared. Okay? You should always check that at the end. Did I even set the formula up right? Did I do pi r squared? It's really easy to miss this square if you don't ask the question. Okay, so now that we're set up, let's integrate this thing. Let me just rewrite here. I can pull the pi out. So I have pi integral from 0 to 1/2 of, if I square this guy, 1 squared, of course, is 1. And the fourth root of 1 minus x squared squared is the square root of 1 minus x squared dx. And of course, the antiderivative of 1 over the square root of 1 minus x squared is sine inverse of x. So this is just pi times sine inverse of x evaluated from 0 to 1/2, which is the same as pi times, if I plug in a half, I get sine inverse of 1/2 minus sine inverse of 0. Okay, so this is pi times, what is sine inverse of 1/2? Well, that would be the angle whose sine gives me a half. And sine of pi over 6 is 1/2. So this must be pi over 6. And then minus sine inverse of 0, or in other words, the angle whose sine is 0, which is 0. So I get pi times pi over 6, which is the same as pi squared over 6. So that's the cubic volume of this shape that we formed up here.